Hey everybody, welcome to this video about Pigeonhole Principle, which falls into our techniques of counting discussion. Now, Pigeonhole Principle is a little oddly named, but it can be very helpful when we see it in an application. I have this thing highlighted here, which is basically says it's a tool to determine what must happen given certain conditions, which is really vague. But basically what we're talking about is what happens when we're trying to distribute objects into boxes, sets, kind of whatever we see happening. And honestly, I think it's best seen with two immediate examples. So let's get into it. Suppose I have to take 4 tests over 3 days. Now, this might feel a little real coming out of midterms here, but if I have to take 4 tests over 3 days, what can I say happens about when they occur? So let's talk about a couple of things here. Here I have these little kind of trays trying to say, okay, here are my days, when do the tests happen? And I can kind of distribute them just in several different ways. So maybe I have to take 2 on Monday, 1 on Tuesday, and 1 on Wednesday. Or maybe I got really unlucky and they all happened on Wednesday. Or maybe I have 2 on Monday and 2 on Wednesday. These are all different ways to have 4 tests over 3 days. Now, when I'm looking at this says, okay, well, what can I say happens every time? Well, I can't necessarily guarantee that I have a test every day. For example, here, I might not have a test every day, or here. I also can't necessarily guarantee that I have exactly 2 tests on every day, or sorry, on one day. For example, let's look at this one. I don't have 2 tests on that particular day, but we're kind of dancing around what we can actually say, which is that at least one day will have at least 2 tests. And if you think it kind of through, you're like, yeah, that feels right. If I have 4 tests and 3 days, one of them's going to get that, like kind of that last one. So let's try it with where it's not just one more, but maybe a few more. If I have 7 snacks that I'm going to distribute among 3 children, what can I guarantee happens when I distribute those snacks? Well, I would recommend that you draw out these little trays and try it out yourself. But here, maybe I give 2 to 1, 2 to 2, and 3 to child 3. I could give 1 to each of them, and then 3, 4, 5 to child 3. Or maybe I really like child 2 the most. Oops, 4, 5, 6, 7. Give them all to child 2, and so on and so forth, right? Maybe I do 1, 2, 3, 4, 5, 6, 7. Here are 4 different ways to distribute 7 snacks to 3 children. So what can we say? Well, I can't necessarily guarantee that each child gets even 1, right? Because here's a way that they don't all get 1. But I can say something about maybe the one who gets the most. Here the most gets 3, here the most gets 5, here the most gets 7, here the most gets 3 again. And really that's the thing we want to say. At least one child gets at least 3 snacks. Now we have to be a little bit careful here. This is a really safe statement. There might be cases where more than one child gets 3 snacks, but I can only make this statement. This is kind of the most like equitable scenario. And really, if we kind of look at both this one and this one, they are the ones that help us make our statement. And that actually leads into how we can prove the pigeonhole principle. What we're not going to do, but we'll at least talk about. So these are both examples of the pigeonhole principle in action, which basically has to do with how we divide n elements into k disjoint subsets. So I don't know if we've seen the word disjoint lately, but as a reminder, disjoint means that they have no intersection. So for example, a test doesn't happen on 2 different days, or a child doesn't share a snack with another one. So here's the statement of the pigeonhole principle. It says, if we have a set S, so let's kind of run this in an example here, kind of saying, okay, what did each of these pieces mean in one of our examples? We'll do the snacks one. So we have a set S, that's our snacks. Oops. Of n elements. Now for us, that was 7 because we had 7 snacks that we were distributing. We are dividing, or basically distributing them into K disjoint subsets. So that was our 3 children. So think of these as like, okay, you have N elements and you have like K different little trays, and these are what their names are. Not necessarily super important, but what we can guarantee is that one of the sets has at least how many elements in it? Well, it looks a little bit odd, right? Because I have 4 and 3 and I got 2, and I had 7 and 3 and I got 3. So what we're really looking for here is N over K with these little funny bars next door to it. This is what's called the ceiling function. And the ceiling function, and what you want to do with this is round up. So for example, when we had 7 and 3, we had 2 and a third, which rounds up to 3. Now, it's not like typical rounding rules. You always round up with the ceiling. If you want to know how to do this in LaTeX, this is /L seal. And then the other one is R seal to go to the other side. So this says, if you have N objects that you're distributing among K boxes, then at least one of the boxes has at least N over K ceiling. So divide them all equally and then round up elements in it. So really, we kind of see that happening here. We distribute them as equally as we can, and then someone's going to get the remainder. Now, be a little bit careful. When this says one set, it's not exactly 1, it's at least 1. Because if there are 5, then it's definitely true that there's 1. It's just also true that there's more than that. So be a little careful. At least. So how would we prove this statement? We're coming out of our proofs unit. How would we prove this? Well, if we kind of think through what we're trying to show, it really is kind of an existence proof, right? We're trying to show that a certain set has exactly what we want. It turns out that the best way to do this is going to be by contradiction. And maybe pause for a second and kind of think it through, or go read it in the text. It's definitely in there as well. But if you didn't have that many in like kind of distributed among your K sets, you wouldn't have enough objects to begin with. You'd say, okay, I have less than N over K at every possibility. I've got K sets, so now I have less than N elements, and it doesn't work. So take a second and try to prove it to yourself or read the proof that's in the text. But really, contradiction is the way to go here. So let's try using this now that we kind of know where we're going, and maybe don't have to draw all those examples out every time, but rather can kind of lean on the statement. So use pigeonhole principle to explain why a function f, which maps from the set of numbers 1 to 10, right? So this, remember, is 1, 2, ... 10. And this is 1, 2, ... 7, cannot be 1-to-1. Well, we're going to need to talk about this as distributing objects among boxes. So really, if we think about a function, right, and it has 1, 2, ... 10, kind of going from here, and then we're going to map over 1 to 7. How do we think of this as putting objects into boxes? Well, when we define our function, we're going to kind of take an element from the domain and we're going to map it to the codomain. Really, if I was maybe putting that in 2, you can maybe see where this is going. I'm putting the element 1 into box 2 if I'm picking that 1 maps to 2. And maybe 2 goes to element 5 or something. So 4, 5, 6, 7. Here are the values of the codomain. And then the objects that I'm putting in are elements of the domain. So maybe I map 2 to 5 is what we said, and maybe 3 goes to 6, and so on and so forth. So what I'm doing is distributing 10 objects into 7 boxes. Now, Pigeonhole principle states, excellent, you're trying to divide 10 objects into 7 boxes. Fantastic. I can guarantee you that there are going to be 10/7 ceiling objects in at least one of the boxes. So if we actually go and calculate this out, this is 2. Right? And it, it's a decimal that we round up, but it's definitely more than 1 and not quite as many as 2. So we round up to 2. So that means 2 objects in the same box. Now, as we read that, we have to reinterpret it back to the point of the question. 2 objects in the same box means that 2 domain elements get put into the same codomain box. That means that 2 inputs have to go to the same output, which means this function can't be 1-to-1. So we'll kind of write that down here. 2 objects, or we'll say not objects, 2 domain elements go to the same codomain element. Not 1-to-1. So again, Pigeonhole principle. We had to recognize it as a distribution problem, but once we did, really, Pigeonhole principle gave it to us for free almost. All right, let's try another example. So there are 27 people in this course. How many people must get the same grade if I give letter grades of A, B, C through F? Well, again, highly recommended trying to figure out how we are distributing these objects into boxes and really what is each one in each case. So I say, all right, what are the objects? What are the boxes? Now you can think of this as like a mapping problem, kind of like we did before, in that students get mapped to their grade, right? You know, we have our things and we have our letter grades over here. And you can kind of use the same description up here as well. But if you're like, okay, I'm just going to put each student into their like grade box, that would work too. So the objects here are students. You're not objects, but in the context of the problem. And the boxes here are their letter grades. So if I have, oops, well, kind of do it this way. There are 27 of these. There are 5 of those. As I distribute them, Pigeonhole principle says there is at least one box with at least this many people in it. So this ends up being 6. So in this context, there will be at least 6 people who get the same grade. People get the same grade. Cool. So a little kind of forewarning paragraph here, which is often that there will be cases that completely exceed the amount that we get guaranteed, right? Maybe everybody gets A's, or maybe everyone, like this whole function maps to the number 1. That's okay, but I can't guarantee that that happens, right? So really all I can say is that this smaller number is what happens for sure. Now, with that in mind, we can kind of reverse engineer a couple of questions about Pigeonhole as well. So for example, How many people do I need in a room to ensure that two of them have the same birth month? Well, let's think about what would be happening if we were trying to do this with Pigeonhole. Well, so we'd have our January and February and March, blah, 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 all the way down to December. So here we would have 12 boxes. And I like to think of it as kind of a game where it's like a worst case scenario game, saying, hey, okay, I could have one person in January and the next person would be in February and the next person would be in March, and still no same birth month, still no same birth month. We'd get all the way down to December. And then the next person, no matter who they are, is going to tip the scales to be in the same birth month, right? So we have 12 months, we have those 12 people, and then that 13th person will guarantee. Which kind of makes sense. We have 12 months. And if I need this thing to equal 2, right? 2 people in the same birth month, all I need is the 13 up here, right? As soon as we're over 12 by a little bit, it's 13 over 12, it's 1 point a little bit, and ceiling tells me to round up. So I need to say, okay, that next person is going to tip me over. So what about the second part of this question? How about 3 people with the same birth month? Dot, dot, dot. January, February, all the way to December. And you can either think of it like kind of putting each person in and then having one person tip over, or you can think about it with the fraction. Really, you want like 2 per, and then that next person, which would be 25. So, right, so 2 per birth month times the 12, so 24, and still not have it happen. But then that 25th person, no matter what their birth month is going to tip the scale. From an arithmetic standpoint, if I want this to be 3, then I just need to be a little more than 2, which is 25. So what happens if it gets a little more complicated? So here we have a bag with 4 different colors of marbles in it. Maybe we'll say red, yellow, green, and blue. How many do we need to pick to ensure that we pick 6 of the same color? Well, orange, red, yellow, oops, that's not a G, green, and blue. I want to pick 6 of the same color. Well, if I have 4 and I need this to equal 6, try it out, see what you can find. Again, you can always pause this video and think about it for a second. But if you've thought about it, well, really what we're looking at is kind of 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 2, 3, 4, 5, kind of the worst case scenario in every single case. Like I have 5 red and 5 yellow and 5 green and 5 blue. I've gotten super unlucky, or maybe super lucky, depending on what the rules of the game. But I have everything almost there. That last marble, that 21st marble, is going to be what kicks me over. And again, we see it in the fraction. 20 divided by 4 is 5, but 21 divided by 4 is a little more than 5, which rounds us up to 6. So Pigeonhole principle would state that we have to have at least 6 in any particular color. But what if it's not even, right? So for example, here I have this same bag of marbles. There's 4 different of each. How many marbles do we need to pick in order to ensure that we have 3 red, 2 blue, 4 green, or 5 yellow? Well, it turns out that it's very similar. Red, yellow, green, blue. It turns out that it's very similar. What we're looking for, though, is that like the worst case scenario, or kind of almost there, but not quite, is different for each tray, right? So maybe 2 red and, oops, I did this in the wrong order. All right, 5 yellow would be 4 yellows, and then 3 greens and 1 blue. So in each of these cases, we are almost there. Whatever the next marble would be what would kind of send me over the edge, right? So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The 11th marble will do it. So we need a total of 11. Now be a little careful. We can't necessarily kind of think about this as just the total number divided by that, right? Because like 11 divided by 4 doesn't give us like one of these cases. In general, if you had, you can kind of do a little bit of side work here. Let's say you had like, you needed ni of color I, right? So like you needed 3 of color 1 or 2 of color 2 and so on and so forth. So we're tossing in some letters here. If we needed ni of color I, you might then think, okay, what we need is ni minus 1. So 1 fewer than are required. I equals 1 to, we'll say we had k colors total or something like this. So basically 1 fewer than you needed across all different colors, add those all up, and then add 1 more, right? So here we needed 3 of red, so that's why we did 2, that minus 1, and so on and so forth. We added them all together and then had that last kind of tipped marble. So here, this is it kind of in general, provided we kind of see where we're going. So the last example we're going to do, I listed 2, but we'll just do the first one because this one actually is written in your book if you want to go take a look, is pigeonhole principle applied to something a little weird. So go with me on this for a second. I have a party of 6 people. I want to show that there are either 3 people who all know each other or 3 people who don't. How do we think about this? Well, suppose we have our 1 person. You know, we'll say, okay, we got our 1 person, he's sitting there. Then there are 5 other people. And what we really want to see here is maybe I'll draw them out with little dots. We divide them into 2 categories. Either they know our person or they don't. Oops, I'll be a little more careful here. So our special person, these 5 people are going to get divided into 2 boxes. Either they know our person or they don't. So pigeonhole principle tells me that these 2 boxes each have at least 2 people in it. Or sorry, at least 1 box has at least 2 people in it. Oh, no. 3 people in it. Oops, my bad. Can do arithmetic. So the 5 divided by 2 is 2.5, right? So we round up. At least 1 box has 3 people in it. This is great news for me, right? Because really, I have 3 people who either know each other or 3 people that don't. So if it's the case, so let's say, okay, we have our 3 people in that particular box. And we say, all right, well, they either all know this 1 person or they don't. Well, what does that mean? Well, either we have these 3 people that all know that person or they don't, right? So if they know each other at all, we're good to go. So if any 2 of these people know each other. So let's suppose that it's the known box, because the similar case would happen if it's the don't know box. So they say, okay, yeah, I know this person. If any two of these people know each other, great, we've got our set of three, right? So we could say, okay, maybe we'd say, all right, these people know each other and they both know this person, we've got our set of three, we're good to go. If no one knows each other, great, we've got our set of three people that don't know each other. So in any of these cases, you'll find that this will work. So you can definitely argue it to yourself a little bit. Why do we care about this? Why does it seem a little weird? It turns out this is related to a theory of mathematics, specifically graph theory, called Ramsey theory. Now, I think it's in Jay's proof book if you're a little curious about this. But what this really proves is something like this. Is a little bit odd. So it says if you have three people that either all know each other or all don't know each other, you need 6 people at your party. I can design a party of 5 people where that doesn't happen. So it's kind of a weird reverse pigeonhole principle. It turns out that this question is really hard to answer in kind of its generality. So just kind of a fun exploration. Don't worry about it too much or anything. But pigeonhole principle can be applied to research level mathematics as well. So hopefully we kind of understand now how to distribute objects into boxes, read over pigeonhole principle. Please bring your questions. Thanks for kind of putting up with the video this time, and I'll catch you on Monday.